Three-phase motors are used because they run on very high voltage and as a result allow a lot of current, and as a result they generate a lot of torque. As a result they are used extensively in heavy machinery like lathes, milling machines and drill presses. The squirrel cage induction motor consists of a stator and a rotor. The stator contains the field coils and the field assembly and is the main driving force behind the motor's operation. The rotor is the section of the motor that actually rotates. There's no electrical connection between the stator and the rotor, and that is the biggest advantage when it comes to the three-phase motor. Three-phase induction motor. Okay, now the construction of the motor. Basically, in the center we will have the rotor. The rotor is mounted on the axis, and we will have conductive rods mounted in the core all the way around, all around the rotor. Okay, these are slightly offset at an angle to the axis to allow for better induction and conduction to take place. Then we will have the field assembly, which consists of a multiple of 3 poles. Okay, so we will have, for example, our red phase connected as the coils on that field assembly. Our yellow phase might be connected onto that field assembly, and then our blue phase might be connected on those field assemblies. These are each connected to a separate phase, and as we recall from the transformers and the generators, we will have 3 signals connected onto those field coils. We will have our red phase connected across the red coils. We will have our yellow phase connected across our yellow phase, and our blue phase will be connected over our blue phase. Now we need to remember that these 3 phases are interlinked or have a relationship with each other. Okay, so my red phase is represented by sine theta. My yellow phase is represented by sine theta plus 120 degrees, and my blue phase will be represented by sine theta minus 120 degrees. Now you're welcome to go do the math behind this, just to double check. Now sine theta at 0 degrees will give me 0, 0, 30, 60 degrees and 90 degrees. Okay, so sine theta at 0 degrees will give me a value of 0. At 30 degrees it'll be at 0,5 or 50% of the waveform. 60%, let's round up or round down, that gives me 0,8 or 80%, and then at 90 degrees we will have 1. At 120 degrees we will have sine at 120 degrees we're going to round down at 0,8 or 80%. Then at 120 plus 30, which is 150 degrees, we're going to have 0,5. 120 plus 60 gives me 180, and sine theta will then give me 0 over there. And then at 90 degrees I will have minus 0,5. Each of these we're going to convert to percentages, and we'll see that why in a moment. So sine at minus 120 degrees is going to be negative 0,8. Then we're going to get minus 1. At minus 60 we're going to get minus 0,8 again, and then at sine of 90 minus 120, which is 30, that'll be minus 0,5. Okay, so each of these I'm going to convert to percentages, because as we know there's a phase shift between the voltage and the current. But if we ignore the voltage for a second and just concentrate on the currents, we will see that at this stage we've got 0% current flowing. When we move to 30%, we've got half the current flowing. When we move to 80%, we've got, oh sorry, at 60 degrees we've got 80% of current flowing, and at 90 degrees we've got maximum current flowing through that specific coil. The remaining coils will experience the same. If we look at our 0 degrees, if we look at 0 degrees, and let's accept that this forms the internal of my stator. The rotor is going to be placed in the middle over there, and let's have a look at the table from just now. Sine theta is at 0 degrees, which means I've got no flux on the left, or on the top and the bottom. On my yellow phase I will have 80% flux, so let's say there's 8, or each 10% is one flux line, so there I'm going to have 1, 2, 3, 4, 5, 6, 7, 8, and on this side 1, 2, 3, 4, 5, 6, 7, 8, 6, 7, 8. Okay, let's just say for argument's sake that's the north side and this is the south side. Then my blue phase, again, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Now let's say this is the north side and that's the south side due to the winding. You'll see that we get a flux direction 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. We get an overall flux direction that looks in that direction. So we've got north on this side and south on that side. Now when we move over to 30 degrees, we're going to have a similar scenario. There's my rotor, or there's the stator. The rotor is going to be inside. And now we're going to have again my rotor's in the middle there. Now my red phase will be at 50%. Let's say north is at the top, south is at the bottom. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. The yellow phase is decreasing in flux to 1, 2, 3, 4, 5. This is still north, this is still south. 1, 2, 3, 4, 5. and then my blue phase has gone up to 100% with a north over here and a south over there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is at 100%. This one is at 50%. And red is also at 50%. So what we can see over here right now, north to south. So we're going to have 1, 2, 3, 4, 5, and then 1, 2, 3, 4, 5, and there I've got my 10, there I've got 5. So now I'm going to go over to there. 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So if I'm comparing this to this, we can see we get a more angled north-south direction occurring, with north on this side, south on this side. Okay, so if this is drawn exactly to scale, we will see that this is 0 degrees, so when we get to 30 degrees, this would have rotated 30 degrees up to the top like that. We'll post a picture so that it's a scaled picture so that we can see it more clearly. Now when current passes through the field coils, a magnetic field is created. This magnetic field is directly proportional to the amount of current that flows, and because these three phases are at 120 degree intervals, the magnetic field strength and the polarity of the 6 fields of the coils will differ. Additionally, the 3 phases are all connected to an alternating current, which means that the magnetic fields that are created are constantly changing. These changing magnetic fields will be focused on and cut across the rotor's conductive rods, thereby inducing a current into those rods. The current in these rods of the rotor will create their own magnetic fields. These magnetic fields react to the magnetic fields of the stator, and this causes a force between the magnetic fields that causes a rotation. The rotation is maintained by the continuous changing of the polarity of the stator, and thereby the rate of rotation is controlled very closely to the frequency of the supply. The rotating magnetic field is a concept whereby the stator is supplied with a changing magnetic field. The field coils stay stationary, but because of the change in the supply voltage, the magnetic fields change in strength and polarity, which has the effect of making the magnetic field seem to rotate.